Well, we're moving right along. Again, hopefully you just clicked over from the last video. And now we're going to talk about net ionic equations. So this is a concept that you may not have heard before, but I think it's one that's pretty simple as we do some examples together. So let's consider the reaction of solutions of silver nitrate and sodium chloride, okay? So they're shown here, right? Silver nitrate and sodium chloride. We can ask the question, what is the particulate level composition of each solution before the reaction occurs? Well, one thing I'll say before we answer that question is, if you remember, this guy here, this AQ, means aqueous, or that this compound is dissolved in water, okay? So since it's an ionic compound, when it's dissolved in water, it's going to break apart into silver ions and nitrate ions, which is something we saw, I believe, 2 videos back in this chapter. So at the particulate level, right, we're going to have silver ions and nitrate ions, and we're going to have sodium ions and chloride ions. Okay? And so then that's how it is on the particulate level, right? Each solution before this reaction occurs, you have these ions floating around in solution. But the question is, how are these represented in a conventional equation, which is what we've been using so far when we were doing things like single replacement reactions and double replacement reactions. We've been using conventional equations, and well, we might write it like this in a conventional equation, right? We'd have silver nitrate plus sodium chloride, and then we'd write the products, right? So that's how we've been writing it so far, okay, in the conventional equation, but it's not capturing the particulate level composition. And we're going to see why that's going to be a problem in a second. So, well, I guess in the next slide, we're going to see where it's going to be a problem. So the problem is that it doesn't tell us the true composition of the solution, which is the ions. So to avoid this misrepresentation, which is going to be important as we go on, we can write the formulas of the reactants as they actually occur in solution. So again, a silver nitrate solution, which is what that AQ means, or aqueous, is going to be silver ions and nitrate ions. Same idea here, a sodium chloride solution, okay, you're going to have the sodium ions and the chloride ions, okay? So this is how we're going to represent solutions of these ions. And you can tell that it's a solution by this little AQ written down here. Okay, so we can perform similar analysis with the products of the reaction. So if you did the double replacement reaction, you would get silver chloride precipitate, okay, which means solid. And the symbol we're going to use for that, okay, is just an S. This is something we saw before, okay. And sodium nitrate solution, okay. So this is going to be aqueous. Again, it's the solution. So again, the conventional representation of the products is what I just wrote there. Okay, we're going to have this silver chloride and sodium nitrate. But again, it doesn't capture the whole picture of the species that are really in solution. The products as they actually occur is going to be silver chloride and sodium ion, and then nitrite, or nitrate, excuse me, I said nitrite, it's nitrate. Whoop, I don't know why that's acting up. I want to write an AQ there, ions. Okay, now notice I didn't break up the the silver chloride here, and that's because it is a solid, and that means it's not dissolved in solution. It's stuck together, okay? So with aqueous things, they're dissolved in solution, so the ions break apart. For solid things, you do not break them apart into their ions, okay? So that's a key, all right? Solid things, all right, or precipitates stay together, okay? They're not dissolved in solution by definition, okay? So these are the products as they actually occur in the solution, okay? After the reaction. Now, let's go through it step by step. Okay, so let's start up here at the top, the conventional equation, okay? Again, we're gonna have, if I could just turn the page here for myself, so I don't forget, we're gonna have silver nitrate plus sodium chloride. That's supposed to be an AQ, okay? Gives me, let me move my screen here. Silver chloride, solid, plus sodium nitrate aqueous. Okay. Can I try to fix that guy? Is it even worth it to try? I think it's worth it to try. So yeah, there we go. Okay, so that's the conventional equation. And that's what we've been using up to this point in the class to represent chemical reactions. And it's good for stoichiometry problems like we talked about in chapter 10, converting grams of one substance to grams of another substance, but it lacks information about what's really happening in the solution, okay? So to represent what's really going on in solution, we could write something that's called the total ionic equation, which is where you break apart all the compounds that are aqueous into their ions and represent them that way. And we did that on the previous two slides. So I'm just going to kind of write and bring together what we learned. So again, everything that's aqueous over here, we're going to break apart into its ions. If we did that, we'd get silver ion, aqueous, plus chloride ion, aqueous, plus sodium, aqueous, plus chloride, aqueous, gives me silver chloride, which is a solid, stays together, plus sodium ion, plus the nitrate ion. Okay, that is not an AA, that is an AQ, okay? My pen, I guess, maybe isn't as sensitive enough to write that. Okay, there we go. So again, this is the total ionic equation and represents each species as it actually occurs in solution. Okay, so that is a key there. Okay, this is our total ionic equation. Now the title of this video is net ionic equation. So what are those? Well, before we get there, okay, let me just write down exactly what I wrote down before. I should have just did it already. AQ plus nitrate. So bear with me. Sorry, I should have just had this already written down. Okay, let me just move my screen for a second. Whew, okay, so that's the total ionic equation. Wrote it kind of fast, so it might be a little messy, but that's the total ionic equation. Notice now there are species that occur on both sides of the reaction. Okay, so they're a reactant and they're a product. And if I look here, we see I have the nitrate ion over here and a nitrate ion over here, a sodium ion here, and a sodium ion here. They're exactly the same in the total ionic equation. Okay, so these guys, these species, nitrate and sodium. Okay, and again, AQ or aqueous says that they're dissolved in solution. They're the same. So neither of these species undergoes a chemical change. Oh, my goodness. Being a mess today. Okay, neither ion undergoes a chemical change. All right. So if you eliminate the non-reacting ions, which we call spectator ions, what remains is the net ionic equation. Okay, so if you just take these guys out, all right, on both sides of the equation, what we're left with is what's really going on in solution, which is silver ion plus a chloride anion gives me solid silver chloride, okay? And this is what we refer to as our net ionic equation, okay? So again, not too difficult. You just have to be able to write the total ionic equation, then look on either side of the equation to see what species are on either side that are the same. They're the spectator ions. You get rid of them and you're left with the net ionic equation. So let's do two examples, I believe, where hopefully this becomes more clear if it's not clear already. Okay, let's see here. This is just basically, I think I just jumped ahead in my explanation, but I don't need to write anything here. So this reaction and then the net ionic equation. So I won't write anything here, but it just is reiterating what I said. Maybe I wrote too early in my explanation. Okay. So before we do examples, here's just what we're going to do here. Here's some rules that you can refer back to. So first, you write the conventional equation, including state symbols, like if it's a gas, a liquid, a solid, or aqueous, and you need to balance the equation. That is key, all right? Always make sure you balance the equations. We want the same number of ions and species on either side. Then you write the total ionic equation by replacing each aqueous substance that is a strong acid or ionic compound with its major species, which are the ions. You don't want to separate weak acids into ions, even though its state symbol is still aqueous, because we know a majority of those still remain as molecules. Also, this is really the key, never change solids, liquids, or gases into ions. Okay, be sure that the equation is then balanced after you do that. So after you write the total ionic equation, remove the spectators, and then you're left with the net ionic equation. Okay, and make sure that it's balanced at the end and that you're using the lowest possible coefficients in front of your species. Okay, and we saw that from balanced chemical equations. Okay, so this chart is something we're going to refer back to, or you're going to use. It's a solubility chart of ionic compounds. And this will help you, and it'll be on the final exam. It'll help you determine if, when you put two ions together, if you form a solid or if you form an aqueous species. For example, let's say I have the cobalt-2 cation, and I put it with the chloride anion, okay? If I look at my chart, the resulting compound will be aqueous, okay? However, if I put the cobalt-2 cation with the carbonate anion, okay, it will be a solid, okay, the resulting compound. So again, this is something that you can refer back to. You just look at the chart, you look at your cation, you look at your anion, and you find whether it will be aqueous or a solid, okay? So let's do an example problem together. So we need to write the conventional equation, total ionic equation, and the net ionic equation for the following reactions. Okay, so we have nickel 2 nitrate or nickel nitrate plus sodium carbonate gives me solid nickel carbonate and sodium nitrate. Okay, so I'm just going to write the conventional equation on the top. It's something that we've had a lot of practice doing already, and we did that whole lab where we just did these types of problems. So I'm just going to write it on the top, assuming we've had plenty of practice. So we have nickel nitrate plus sodium carbonate gives me nickel carbonate. And it says it's a solid, so I'll just put that there for now, plus sodium nitrate. Okay. And then if I balance this chemical equation, I believe I just need a 2 in front of the sodium nitrate. So I have 2 sodium ions on either side, 2 nitrate anions on either side, 1 nickel on either side, and 1 carbonate on either side. Okay. Now, I notice I didn't write the term or the state symbols under the nickel nitrate and the sodium carbonate. So you can go back here. I'll just erase what I wrote already. Okay. So you look on the chart, like I said, you say, all right, nickel is here and nitrate is right here. That is going to be aqueous. Okay. And then sodium nitrate, right, is our other compound over there. So you look, sodium is down here. It's aqueous as well. And then sodium carbonate, sodium is here, carbonate is here. It is also aqueous. So everything here is aqueous. Aqueous, aqueous, okay? And aqueous. Okay. So again, that's how you will use the chart. All right, so that's the conventional equation. Check. So now let's write the total ionic equation. So we're going to break these apart into their ions now, everything that's aqueous. We're going to leave everything that's solid together. Okay, so we're going to have the nickel, okay, and we're going to just split it right down there. So nickel plus 2 nitrates, and nickel has a 2+ charge. The nitrate here has a 1- charge. So this is just going back to our videos on ionic solutions. We're just doing that. Each one we're writing its ionic species plus 2 sodium ions. Okay. So sodium's a +1 charge, and I need 2 of them because the carbonate anion is a 2- charge, and the compound needs to be neutral in its final state. Nickel carbonate, that stays together, plus 2 sodiums plus 2 nitrate. Okay, so this is our total ionic equation now. Okay, I broke up every species that was aqueous. I left together those species that are solid, which is the nickel carbonate. Okay, well, if I want the net ionic equation, what do? Well, I examine and look at my spectator ions that are on either side of the equation. And I believe here we have nitrate, okay, 2 nitrate anions on either side of the equation, and 2 sodium ions on either side of the equation. Okay, so those are my spectator ions. So I could cancel them out, okay, get rid of them, and write my net ionic equation, okay, which is going to be a nickel ion plus a carbonate ion, and that gives me nickel carbonate solid. Okay, just double check to make sure it's balanced, all is good. So that's my net ionic equation. Okay, so this is the net. Okay, this is the total. And this one on the top, like I said, is the conventional. Okay, so that's an example. Let's do one more. Okay, again, write the conventional total ionic and net ionic equation for the following reaction. Okay, so now we have magnesium metal plus iron 3 chloride gives me magnesium chloride and solid iron. So why don't you pause the video and try to do this one on your own, and then we'll go through it together. Okay, so let's start with the conventional. So let's say that's 1. So we have magnesium metal, okay, that's just going to be a solid, plus iron 3 chloride, which is aqueous, gives me magnesium chloride. Whoops, I messed up. Which is also aqueous, plus solid iron. Okay, now we need to balance this equation. Okay, and when you do that, I believe there's a 3 there, a 3 there, a 2 there, and a 2 there. So now I have 3 magnesiums on either side of the equation, 2 irons on either side of the equation, and 6 chloride ions on either side of the equation. Okay, so that's my conventional equation. So now let's do the total ionic equation. Okay, so again, leave together everything that is a solid. Okay. Break apart everything that is aqueous. Okay. Now, this is my total ionic equation, and you could check the ions, right? 3 magnesium, or the elements, I should say, 3 magnesium, 2 iron, 6 chlorine, 6 chlorine. So it's balanced, the elements. Okay, so now let's do the net ionic equation. All right, so we're going to look at our spectator ions, and you might be tempted to say, I have magnesium on this side, magnesium on this side, they cancel. But that's not true because look, the magnesiums are in different states here. On the reactant side of the equation, the magnesium is a solid. On the other side, it's aqueous and it's an ion. So you can't cancel out the magnesiums. It looks like the only thing I can cancel out is these chloride ions. Okay, so these are my spectator ions. So get rid of them. And what I'm left with is 3 magnesium plus 2 iron gives me 3 magnesium plus, let me move my little screen here, 2 iron. Okay, so this is the net ionic equation. So there's going to be plenty of examples, I don't think this week, but next week in the homework of going through and doing net ionic equations, but hopefully that helps, and I will see you next week in more videos on Chapter 9.